next chapter in power electronics, that is power semiconductor devices. Okay. In power semiconductor devices, I want to discuss so many devices like diode, thyristor, triac, diac, GTO, BJT, MOSFET, IGBT, G. All these devices I want to discuss. First, I will start with power diode concept. Okay, that is mentioned in the syllabus in various competitive exams. Important. Okay. Then, before starting, what exactly power diode? What is the construction details of power diode? And what is the characteristics of power diode? Before that, I want to give some introduction here. Some basics I want to give. This basic concept is required to analyze in detail about each concept. Okay. Then, with respect to power semiconductor devices in the power diode, I want to give some introduction. Okay. Some introduction concept I want to explain here. Okay. This is some introduction concept with respect to power semiconductor devices. Okay. We know that here I am explaining the power semiconductor devices means. We know that which group elements are used as a semiconductor devices. Which group elements are used as a semiconductor devices. Just not giving in clear about semiconductor physics. Just before starting these different types of power semiconductor devices, I want to give some introduction. Understood? We know that fourth group elements is used as a semiconductor devices. Is used as a semiconductors. Fourth group elements are used as a semiconductors. Which are the fourth group elements? Carbon, yes, silicon, germanium and lead. In carbon, silicon, germanium and lead, again, which is more preferable? Yes, silicon and germanium is more preferable. As compared to carbon and lead, silicon and germanium is more preferable. Why the silicon and germanium is more preferable? Because these are abundant in nature, more available in nature. That is more preferable because of abundant in nature. Abundant in nature. These are abundant in nature. Silicon and germanium is more preferable because these are abundant in nature. But in silicon and germanium, again, which is more preferable? Silicon is more preferable. As compared to germanium also, silicon is more preferable. Why the silicon is more preferable? It is less temperature dependent. It is less temperature dependent. As compared to germanium, silicon is more thermally stable. Understood? That's the reason why it is less temperature dependent. In the selection of semiconductor devices, the device which is less sensitive to temperature, that device is more favorable. In general, semiconductor devices are more sensitive to temperature because of negative temperature coefficient. Understood? Because of negative temperature coefficient, then semiconductors are more sensitive to temperature. But in silicon and germanium, silicon is less sensitive to temperature. That's why silicon is more. Yes, germanium also has so many applications. But I'm comparing like this. Silicon and germanium, silicon is more favorable as compared to germanium because of less temperature dependent. Okay. We know that all the semiconductor devices are having, in general, these are negative temperature coefficient. They also design with positive temperature coefficient by making some alloy, but generally semiconductors are having negative temperature coefficient. Negative temperature coefficient means if the temperature is increases, then resistance will be reduced. In all the semiconductors, if you draw the characteristics between, resistance versus temperature characteristics, we can get the characteristics like this. In the case of which one? Semiconductors. This is in semiconductors. Similarly, if you draw the characteristics between resistance versus temperature characteristics, in the case of conductors or metals, then it is if the temperature is increases, resistance is also increases. This is for metals or conductors. This is positive temperature coefficient. This is a negative temperature coefficient. Negative temperature coefficient. Okay. Then in silicon and germanium, silicon is more favorable because of less temperature dependent. Yes. Another point to remember. All these devices or elements having less conductivity at room temperature. Having less conductivity at room temperature. Having less conductivity at room temperature. Yes, having less conductivity at room temperature. Now, and these are called having less conductivity at room temperature, and these are called or these are acts as intrinsic semiconductors. Intrinsic semiconductors. These are called intrinsic semiconductors having less conductivity at room temperature. Now, in order to improve the conductivity of these elements or these semiconductor devices, the external impurities are added. The process of adding of impurities is called doping. Understood? That means to improve the conductivity, what we are doing? External impurities are added. External impurities are added. External impurities are added. External impurities are added. The process of adding of impurities is called doping. The process of adding of impurities. The process of adding of impurities is called doping. The process of adding of impurities is called doping. This is fourth group elements having less conductivity at room temperature. To improve the conductivity, we are adding external impurities. the process of adding of impurities is called doping. Then what are the impurities we are adding means? Mainly we are adding two types of impurities. One is trivalent impurities and pentavalent impurities. We are adding two types of impurities for fourth group elements for intrinsic semiconductor. That is nothing but one is a trivalent impurities and other one is a pentavalent impurities. Now tell me, this okay? This fourth group elements, intrinsic semiconductors, to improve the conductivity, external impurities are added. The process of adding of impurities is called doping. The process of adding of impurities is called doping. Now tell me, for fourth group elements, if we add third group elements, if we add the third group element, that is third group impurities, that is trivalent impurities. That is for fourth group elements, if we add third group, that is trivalent impurities, trivalent impurities, trivalent impurities, trivalent impurities. Then it becomes a which type semiconductor? It becomes a p-type semiconductors. Okay. Then which is the trivalent impurities? You tell me. Which is the trivalent impurities? Yes. One is boron, aluminium, gallium, indium. All these are trivalent impurities. Then it becomes a p-type semiconductor. For fourth group element, if we add fifth group element, this is pentavalent impurities. Pentavalent impurities. Pentavalent impurities. Then it becomes a which type semiconductor? N-type semiconductor. Then what is the pentavalent impurities? You tell me. What are the pentavalent impurities? S. One is phosphorus, phosphorus. The another one is arsenic, antimony, bismuth. This is pentavalent impurities. Then it becomes a N-type semiconductor. Then after adding external impurities, then this semiconductors becomes which one? P-type and N-type. The semiconductors becomes P-type and N-type. This P-type and N-type semiconductors are called extrinsic semiconductors. These are called extrinsic semiconductors. These are called extrinsic semiconductors. This P-type and N-type semiconductors is called extrinsic semiconductor. Then in P-type semiconductor, which is the majority carrier? Which is majority carrier? Majority carriers are holes. Majority carriers are holes. Then which is the minority carrier? Then minority carriers are which one? Electrons. Minority carriers are electrons. Okay. Then in the case of N-type semiconductor, which is the majority carrier? Majority carriers are which one? Electrons. Majority carriers are electrons. Then which is the minority carrier? Minority carriers are holes. Minority carriers are holes. Holes are the minority carriers. holes are the minority carriers. But point to remember, this is p-type semiconductor layer and this is n-type semiconductor layer. After adding external impurities to the intrinsic semiconductor, then it becomes a extrinsic semiconductor. Then this extrinsic semiconductor is a p-type layer and a n-type layers. Okay. Now, based on the doping concentration, this layers are represented like this. If it is represented like this p comma n layer, these are called moderately doped layers. If it is represented like this, then these layers are called moderately doped layers. Okay. If it is represented with p plus comma n plus n, then these layers are called heavily doped layers. Based on the doping concentration, these are called heavily doped layers. These are called heavily doped layers. Then if it is represented like this, p minus and n minus, then these are called lightly doped layers. Okay, understood? But point to remember, a lightly doped n minus layer is called intrinsic layer. A lightly doped n minus layer is called intrinsic layer. Now, after forming the p layers and n layers by using external doping, then by adding this p and n layers, then we can get one of the device that is nothing but a PN diode. Okay, by adding this p and n layers, this okay, understand this one. Then by adding this p and n layers, we can get a PN diode. Okay. Now we concentrate on first one is a signal diode. Once you are forming this p layers and n layers, by adding this p and n layers, then we are getting one metal junction. This is p layer and this n layer. Then it is called PN diode. Okay. Then having two terminals, anode, cathode, having one junction. That's why in general it is nothing but a one diode. Then what is the symbolic representation of diode? This is anode, this is cathode. This is a symbol. What is the symbol used for the diode? Symbol. Okay. Then this is nothing but a PN junction diode. That's why a diode is, in general, it is a two terminal, that is anode and cathode. Two terminal. One junction. Two layer. Yes, bistable, uncontrolled, unipolarity, unidirectional, it blocks only one polarity, and unidirectional, device. Okay. It is a two terminal, one junction, two layer, bistable. Bistable means it is having two states. One is on state and other one is off state. Okay. Bistable, uncontrolled, unipolarity means it blocks only one polarity. Unidirectional, bipolar device. That is, the conductivity is due to both majority and minority carriers. That is bipolar device. Okay. It is operated in two states, that is on state and off state. If VAK, if anode to cathode voltage positive, then diode is under forward bias. If VAK is negative, then the diode is under reverse bias condition. That means if the diode is forward bias or reverse bias, not only depends only on anode voltage, not only depends only on cathode voltage, it depends on both anode and cathode voltage. This VAK is positive. For example, if the diode is connected like this is 5 volts and this is 2 volts. And if it is connected like this is minus 5 volts and this is minus 10 volts. If it is connected like this is minus 10 volts and this is minus 5 volts. The diode is forward bias or reverse bias, not only depends on only anode voltage, only cathode voltage. It depends on both anode and cathode voltage. For example, if VAK, in this case, VAK is nothing but a VA minus VK. Okay. VA is how much? 5. VK is how much? 2. That is 3 volts, positive. Then diode is under which condition? Forward bias condition. Okay. If VAK, that is, what is VAK here? Minus 5, minus half, minus 10. That is plus 5. Then diode is under forward bias condition. Now we calculate anode to cathode voltage here. Minus 10, minus half, minus 5. This is minus 5 volts. Then diode is under reverse bias condition. That's why the diode is forward bias or reverse bias. Not only depends only anode voltage, only cathode voltage. It depends both anode and cathode voltage. Then VAK is nothing but a VA minus VK. Okay. The name is given as signal diode. These diodes are used. Then the name is given as a signal diode, used at signal level. Used at signal level means that is used at signal level. That is used at signal level. Signal level means for a voltage of plus or minus 15 volts to plus or minus 30 volts up to. For a current of milliamperes to few amperes. Milliamp. Then for power of milliwatts to few watts. That is nothing but a range of voltage, current and that. The name is given as a signal level. Signal level means maximum we can use up to 30 volts. Only small wattage it is preferable. Current is small amperes only it is preferable. That is the name given as a signal diode. Okay. This is some introduction to the what exactly the concept of in power semiconductor devices, which devices are used as a semiconductors, then what exactly signal diode. Okay. Once we are forming the extrinsic semiconductor, then by adding this P and N layers, then you can get one of the useful device, that is nothing but a diode. Then it is nothing but a PN junction diode. A PN junction diode. Then this signal diode is name is given as a, this range of voltage, current and powers we are preferring. But now the concept is, what is the need of implementing power diode? What are the constructional features of power diode as compared to signal diode? Then what are the characteristics? we are analyzing in the case of power diode. That I want to discuss. Okay, this is some introduction only. Okay, then you start with concept of power diode. Okay, now see what the concept of power diode is. Understood? Okay, then start with the concept of power diode. But before that, one note you remember here, very important observation. This note you remember as a note. This you remember as a note. Throughout analysis of semiconductor devices, we can use this concept. Okay, that means if the doping concentration is increases, if the doping concentration is increases, the doping concentration increases, if the doping concentration is increases, then if the doping concentration is increases, then what is the conductivity? Conductivity is increases, and conductivity is increases. Then what is the depletion layer width or layer width? Layer width is reduces. Sorry, yes, layer width is reduces. Then what is the blocking voltage capability? Blocking voltage capability. Blocking voltage capability. Blocking voltage capability is reduces. That means if the doping concentration is increases, conductivity is increases, layer width is reduces, blocking voltage capability is reduces. That is, a lightly doped layer, a lightly doped layer blocks high voltage or less voltage? Yes, it blocks high voltage. High voltage. If the doping concentration is increases, blocking capability is reduces. Here I am telling that lightly doped layer blocks high voltage. This point you remember. Okay. Now this, see the concept of power diode. What is the need of implementing this power diodes? Yes. Okay. Listen to this. A high power rating diode is required to carry the high currents in conduction state with less power loss, and to block the high voltage in reverse bias condition. With that motivation, we are implementing the power diode. What is the need of implementing the power diode means? A high power rating diode is required to carry the very high current during the conduction, to carry the high current with less power loss, and during reverse bias condition to block the very high voltages. That means very important points here, you concentrate. Now I am discussing the concept of power diode. Yes, concentrate. I am discussing the concept of power diode, very important. That is a high rating, a high power rating diode is required. A high power rating diode is required to carry high currents in forward, required during the conduction, during the conduction. It carries a high power rating diode is required during the conduction. To carry high currents, with less power loss, to carry high currents with less power loss. Another need is to block high voltages, in off state. That is the need of using the power diode. During the conduction, to carry high currents with less power loss, to block high voltages in off state. Now, to satisfy these two features, we can implement a diode with having less doping layers. That means, to implement with these two properties, to satisfy these two properties, then we can implement the diode with having a doping constant, less doping layers. That means, to satisfy these two properties, to satisfy these two properties, these properties, we can implement diodes. With having less doping layers. But if we implement like this, what is the problem is, if it is implemented with only with 2 layers of having less doping, these 2 points will be satisfied. These 2 properties is satisfied. To satisfy these properties, we can implement diodes with having less doping layers. But due to this implementation, if you implement like this, due to this implementation, what happened? Due to this implementation, conduction losses are increases. Because of high resistivity. Conduction losses are increased, but due to this implementation, conduction losses are increases because of high resistivity. Okay, if you want to reduce the conduction losses, means you want to reduce the resistivity. If you want to reduce the resistivity, means then you improve the doping concentration. If the doping concentration is increases, again blocking capability reduces. Okay, but due to this implementation, what I am telling, that conduction losses are increases because of high resistivity. Then to reduce resistivity, what you can do? To reduce resistivity, doping concentration is increased. If the doping concentration is increases, now what happen? Blocking capability reduces. Hence, there is a contradiction between conduction losses and blocking capability. Understood or not? Now what I am telling, one way to implement power diodes is using the lightly doped layers. But the problem with lightly doped layers means it offers high resistivity. Once it offers with high resistivity means then conduction losses are increases. Okay. We want to design the power diode with less conduction losses means we want to reduce the resistivity. If you want to reduce the resistivity means then if you want to improve the conductivity, that means doping concentration. Then if the doping concentration is increases, again blocking capability reduces. Hence there is a contradiction between conduction losses and blocking capability. Now to overcome this problem or to overcome this contradiction, then we can implement the power diodes in such a way that a lightly doped N minus layer inserted in between two heavily doped layers. Then this contradiction will be overcome. Then we can implement the power diode with high blocking capability and less conduction losses. That is to overcome this contradiction. To overcome this contradiction, what we can do to overcome this contradiction, a power diode is implemented by placing a lightly doped N minus layer in between heavily doped P and N layers. To overcome this contradiction, a power diode is implemented. A power diode is implemented by inserting lightly doped N minus layer in between heavily doped P plus and N plus layers. Then this is the construction of power diode. Like this we can implement the power diodes. That this is P plus, this is N plus. In between these two we can place N minus layer. This is anode, this is cathode. This is called N minus layer. This is nothing but a drip layer. This is our intrinsic layer. Drip layer or intrinsic layer or dripped region. This is called dripped region. Understood? Then this construction is having less conduction losses, more blocking capability. How it is, later on we will see. Because of N minus layer, why it is having less conduction losses? Then this construction having less conduction losses and more blocking capability. Okay. This is a drift layer or intrinsic layer, or it is a drift region. This is anode region. This is substrate or cathode region. This acts as a substrate. This is anode region. This is cathode region. This is the drift region. Okay. Then because of intrinsic layer, that's why due to this N minus layer, conduction losses are less or more blocking capability because of the drift layer. That's why one point you remember here. Due to intrinsic layer in a power diode, yes, in a power diode, due to intrinsic layer, what happened? Blocking capability increases. Capability increases and power loss is reduces. The another point to remember, a power diode is how many layers? A power diode is, it is a pin diode having 3 layers. A power diode is a pin diode. A power diode is a pin diode having 3 layers. Understood? Okay. So this about what is the constructional features of power diode. Okay. How we can implement the power diode. Okay. What is the need of placing the intrinsic layer? This is implemented with the drift layer, that is intrinsic layer, in order to reduce the losses and to improve the blocking capability. Understood? Now, for this power diode, if the reverse voltage is applied, what happens? If the forward bias is applied, what happens? That you will see. Understood? For example, if the forward bias is applied to the power diode, and if the reverse bias is applied to the power diode, what happens? Okay. First we will see the concept of a power diode in reverse bias. Yes. A power diode in reverse bias. A power diode in a reverse bias condition. Yes. This we have a P plus, this is N plus, this is P plus and N plus, and this is N minus. This terminal is anode and this terminal is cathode. Understood? Now, if the reverse bias is applied to this, if it is reverse bias means anode to cathode voltage is negative. If you want to make anode to cathode voltage is negative means anode must be connected to negative, cathode must be connected to positive. Then VAK is negative. VA minus VK. VA is connected to negative. VK is connected to positive. Then resultant is negative. Now it is under which condition? Reverse bias condition. Whenever a reverse voltage is applied to the diode, if the reverse voltage is applied to the diode, because of this reverse voltage, now what happened? What is the majority carriers in P layer? Holes. Holes are having which charge? Positive charge. Then what is this? Negative plate. Because of this negative plate, all these holes are attracted. Then this drift region is increased. This side. Okay. All these holes are attracted like this. Then this is the drift region. This is drift layer or drift region. This drift region is increases like this. Okay. Now, this electrons majority carriers. This is positive plate now. Because of this positive plate, all these electrons are attracted by positive plate. Then this drift region is increased in this direction. That means if the reverse voltage is continuously increased, the drift region is increases. The drift region is increases. Understood that? Okay. That means if the reverse voltage is, if the reverse bias voltage, if the reverse voltage is increased, the drift region is increases. A drift region is increases. The drift region is increases. Okay. If the continuously reverse voltage is applied, if the continuously reverse voltage is increased, the drift region is continuously increased. The drift region is continuously increased. Understood? In some diodes, if the reverse voltage is applied, if the reverse voltage is increased, the drift region cannot penetrate into N plus region. Those diodes are called non-punch through diodes. If the reverse voltage is continuously increased, the drift region penetrates into N plus region. That is, the drift region moving up to end of the N plus region. Then those diodes are called punch through diodes. Here we are dividing into two diodes. One is non-punch through diodes and punch through diodes. Understood or not? That means if the reverse voltage is applied, if the reverse voltage is applied, if the reverse voltage is increased, if the reverse voltage is increased, if the drift region, if the drift region, if the drift region, if the drift region, if the drift region cannot penetrate into N plus region, then it is called non-punch through diodes. Non-punch through diodes. Non-punch through diodes. Non-punch through diodes. That means if the drift region cannot reaches to the end of the or cannot reaches to the cathode, then it is nothing but a non-punch through diodes. That is one point to remember. If the reverse voltage is increased, if the drift region penetrates into cathode, then it is called punch through diodes. Then it is called punch through diodes. then it is called punch through diodes. If you see what is the electric field strength variation in non-punch through diodes and punch through diodes, means then we can get the characteristics like this. What is the electric field variation, electric field strength variation in a punch through diodes and non-punch through diodes? Then we can get the characteristics like this. This is the electric field strength variation in the case of non-punch through diodes. Non-punch through diodes. Non-punch through diodes. Okay. Then this is the electric field variation. This is the electric field variation in the case of punch through diodes. This is punch through diodes. Okay. Electric field variation in punch through diodes. Understood? That means in a non-punch through diodes, the electric field strength variation is like this. It is maximum at P plus N minus junction. This is P plus N minus junction. If that drift region, if that field strength is moving towards the end of the layer, end of the region, the field strength is goes to 0. That is, it is maximum at P plus N minus junction. At the end of the region, it goes to 0. But in the case of punch through diodes, nearly the electric field strength variation is nearly uniform. Throughout drift region, the electric field strength variation is uniform. But in the case of non-punch through diodes, maximum at P plus N minus junction, if it is moving towards the end, if it is moving, if the field variation is moving towards, if the drift region is varying towards the end, then electric field strength is reduces. Electric field strength is reduces. Okay, that is about if the reverse voltage is applied to the power diode, what happens? This here we are classifying into two diodes. One is non-punch through diodes and other one is punch through diodes. Understood? Now I want to explain the concept. What is the difference between non-punch through diodes and punch through diodes? Then you go for, if the forward bias is applied to the diode, what happens? If the forward bias is applied to the power diode, what happens? That concept I want to discuss. Okay, understood or not? Okay. This, if reverse bias is applied, what happening in the case of power diode? If the reverse voltage is applied, what happening in the... Now, I want to discuss what is the differences between punch through diodes and non-punch through diodes. What is the difference between punch through and non-punch through diodes? Okay, that you will see. Yeah. Here in one side you write punch through diodes, in another side you write non-punch through diodes. In one side you can write punch through diodes, in another side you write non-punch through diodes.